One final application of the uncertainties is model fitting. Very often you're not just looking at one number, but you're looking at a whole bunch of numbers and trying to fit a curve to them. So for example, let's say you've got a spring and you're adding weight on the bottom of it. The spring is suspended at the top and got some weights at the bottom. As you put more and more weight on the bottom, the spring should stretch. So this is the length of the spring, and this is how much weight you put on it. And you should get a line that goes up something like this. So that's our model, the red line, which will be that the extension of the spring is equal to a spring constant times the mass plus the natural length. So it's a ax plus b type equation for a straight line. And what we want to do is look at the model and the data and see, do they agree? It's always good to plot this, not just look at the numbers, because plotting often will tell you clues to what's going wrong, allows your human brain's great ability to spot patterns to work. So, what do you reckon? What we've done here is each black dot is a particular measurement, so that's how long the length is for a particular mass, and they've got vertical lines through them which are the error bars. These are the standard uncertainties in each measurement. Another thing we plot, should always plot this as well, are the residuals. Residuals are the difference between the data and the model. So you see the lowest two data points lie above the model, up there, the next one's a bit below it, and so on. And so these two are up here are high, and so on. Now, is this a good fit or not? You might think, look, there are a number of data points it completely misses, they're not in the uncertainties. But remember, these are standard uncertainties, so you expect 68% of the time to be outside these error bars. So in fact, if the line went through every single error bar, that's actually more of a worry. Now here are the rules. So by and large, the model should go through roughly 68% of the error bars. Not exactly, but something like that. You should always plot residuals. A residual is data minus model. In the residual plot, roughly the same number of points should lie above and below 0. And in the residual plot, there shouldn't be an obvious pattern. Like, for example, all the points at one end being high and all the points at the other end being low. So let's have a look. Go back here. And so how many points don't go through the lines? 1, 2, 3, 4 maybe out of the points. So that's actually not far off 30% or so, which is about what you'd expect. So the model goes through about the right number of the error bars. That's looking plausible. And if you look here, there's no obvious pattern. Some are above, some are below. It's not like all the ones on one side are above and one on below. So this is actually a pretty plausible fit of model to data. Now let's look at some less plausible ones. How about this? Okay, well, let's apply the first law. What fraction of the data points lie more than an error bar from the model? It's 1, 2, 3, 4, 5, 6. Now, 6 out of, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 6 out of 16. Yeah, that's maybe okay. It's a bit more than the 30% or so you'd expect, but not too bad, so that's plausible. However, if you look at the residual diagram, you can see pretty much all the points over here are low, whereas pretty much all the points over here are high. You can see it up here as well. The red line goes above most of the points down there and below the ones over there. So this fails the third test. There's about the same number of points above and below the line, but there's a systematic trend. In this case, I'd say the slope of this line is wrong. The red line should have a steeper slope, which would get rid of the problem. So, not plausible. Not a good fit. How about this? Now, many people will think this is a brilliant fit. Look, the model line goes through every single error bar. But to the trained eye, that is suspicious. You wouldn't expect the model to go this close to all the points. You'd expect maybe a third of them, 32%, to be outside, only 68% within. Not only does the model go through every error bar, it goes through the central half of every error bar. So it's right in the middle. That is extremely unlikely to happen by chance. It's clearly telling us that the error bars were overestimated. Whoever did this thought that the errors were bigger than they actually are. The model fit might be good, but definitely there's something fishy about the uncertainties. Here the reverse is true. This line only goes through one or maybe two of the error bars, whereas you'd expect it to go through about 68%. So this is clearly not a very good fit. But there's no real obvious systematic trend. There's about the same number of points above and below, so actually probably it's a reasonable model fit. What has happened, I think, is whoever calculated these error bars, the standard uncertainties, got them too small. There's maybe some other source of uncertainty, maybe a systematic uncertainty they hadn't considered, and the real uncertainty should be 3 or 4 times as big. So probably a reasonable model fit, but the uncertainty analysis once again is extremely fishy. Let's try another example. What do you think of this one? Well, let's count how many are outside the error bars. It's 1, 2, 3, 4, 5, 6, 7. 7 out of 16, that's probably a bit high, but maybe acceptable. But if you look at the residual plot, it's a very clear pattern. All the ones in the middle are low, all the ones on the side are high. You can see it here. These curves actually look like a curve, these data points. They don't look like a straight line. So we have a systematic pattern here. Rule number 3 is violated. So I think this is telling us that in fact for this particular set of data, a straight line is not a good fit. You're better off with a curve. And indeed, if we fit a parabola to exactly the same data, it looks much better. And here we've got about the right number of error bars that intersect the line and no systematic trend. So if you see a systematic trend, it might be telling you that your gradient is wrong, or you might be telling you need a more complicated model, a parabola rather than a straight line. But it is possible to go too complicated. What I've done here is taken this set of data, which are actually based on a parabola, but I fit a 12th order polynomial to them. This is what's called overfitting. You fit a model with too many free parameters, and you can see it's trying to fit every wiggle in the line, like it's trying to fit this one going up and that one going down. It's actually trying to fit the noise, because you'd expect data to go up and down because of noise, and if you're trying to fit that, you're overfitting the data. You're trying to fit things that don't need to be fit, it's just noise. This is also a very common human trend. You get some noisy data set like the stock market, and you get all these financial analysts that try and explain why it went up this day and down that day, when in fact it's just random noise. Very common. Signatures of this, once again, if you look at the residual plot, we've gone through every single error bar, and we've gone close to the centre of almost every error bar. So that's either you've overestimated your error bars, or if your error bars are secure, it's telling you you're overfitting the data.